All right, welcome back. We're going to pick up where we left off in Chapter 14 on carboxylic acids. Today we're going to talk about reactions and also esterification. So we've actually seen this reaction before. Carboxylic acids are prepared by the oxidation of a primary alcohol and aldehyde. Again, what I want you to remember about oxidation is two things. One is it's the addition of oxygen to an organic compound, or that's the way we're going to be looking at it in this class, or it's the removal of hydrogen. And I think that's the one that's going to be new to you, that the removal of hydrogen is also considered an oxidation reaction. So let's get a pen started here, and let's go with red. So right here you can see we have an alcohol with the hydroxyl group on the end. Again, R, remember, is just an alkyl group, so we can have it could be ethanol, or if we put an R as a methyl group there, we'd have ethanol and so forth. So again, primary alcohol because this carbon is only attached to one other carbon. So we apply an oxidizing agent, and what happens there is we have the loss of a hydrogen. So you see that these this part leaves. Well, this carbon, this carbon is here. All right, we lose a hydrogen and we form a double bond with the oxygen, and then we have another hydrogen off of the carbon here. All right, so at that point it's an aldehyde. So remember that an aldehyde has an alkyl group, a carbon, and then what makes it an aldehyde is it's only hydrogen on the other side of the carbon with the double bond. You always got, that's the key part, is this carbonyl group right here. But for an aldehyde, it has to have hydrogen on one side, right? All right, more oxidizing agent, and this can happen just in a series of it's not like you're removing this. This is actually happening all in one movement here. If you have a lot of oxidizing agent, it's going to continue oxidizing this aldehyde. And now what we see is the addition of another oxygen. So remember, oxidation is the addition of another oxygen or the removal of a hydrogen. So here we have ethanol, and here's that active component of the functional group, the hydroxyl group. We add some oxidizing agent, and it either converts this alcohol first into the aldehyde, or we could start with the ethanol right off the bat and add oxidizing agent, and we form carboxylic acid. Again, here's the functional group. That's what you got to remember. And again, if you're struggling with the functional groups, let's go back to Chapter 10, look at that table of all the different functional groups, because that's really what you're doing in this first part of this class, is looking at organic compounds. Tell me what classification is. Is it an alcohol? Is it an aldehyde, ketone, carboxylic acid, ester, ether? And then based off of that, start thinking about what the properties are, physical properties, some of the chemical properties. But what we mainly focused on is melting points and boiling points, and that's due to the way the hydrogen interacts with other elements in a compound adjacent to it. Again, hydrogen bonding is really important. Again, we see hydrogen bonding here because, remember, hydrogen bonding occurs when hydrogen is attached to either oxygen, nitrogen, or fluorine. In this case, it's attached to oxygen. So we are going to see some hydrogen bonding here. All right, so the thing about carboxylic acids, you've probably worked with them before. You've had Chemistry 140. You definitely worked with acetic acid. Acetic acid, a very common acid. And so that's a carboxylic acid. We would call it, according to IUPAC nomenclature, we call it ethanoic acid. And so when we take a carboxylic acid and we place it in water, it will ionize. And so what we see here is, it's kind of interesting on this. It says it dissolves in water and will deprotonate and form the hydronium ion. Well, they talk about that, but they don't show it down here. So if you want to talk about it in terms of this this bullet, you should have water here. And so the carboxylic acid reacts with the water, and we get the carboxylate ion. This is going to be really important. We're going to see where this is used to make salts. And then what happens here is this becomes H3O positive. Now there, well, let's put the positive here, take it off there. All right, so there's the hydronium ion. So you go, well, which way should I write it? Should I write it like the way the slide was or the slide is? It doesn't really matter. I mean, if you want to think of it in terms of, remember if you go back to Chemistry 140 or General Chemistry, we talked about Bronsted-Lowry definitions of acids and bases. And if you want to show it as a Bronsted-Lowry definition, then yeah, you definitely need to put the carboxylic acid with water. This is a reversible reaction. And then we have the conjugate base. Remember that? This was called the conjugate base. And this is called the conjugate acid. Now, the way they had it written before, that's an Arrhenius definition, and that's fine too. And we also write that sometimes as when we're getting a little sloppy, that's the way we'll write it according to Bronsted-Lowry, because we're just trying to shorthand note it. So it's up to, to me, if you're going to say Bronsted-Lowry, you ought to put water as a reactant, and you should have the hydronium ion as a product here. All right, just makes it easier to follow. All right, but what I do want to point out, and we already knew this again from Chem 140, so here's a refresher. Carboxylic acids are weak acids. Remember, the only strong acids in water are hydrochloric, hydrobromic, hydroiodic. Those are binary acids, hydrogen with one other element. And then the oxy acids, sulfuric is a strong acid, and nitric acid, and perchloric acid. Let's And again, people will say that the strongest acid you can have in water is the hydronium ion. All right. So those are the 6 or 7 strong acids in water. And again, what makes it a strong acid is because it completely dissociates into hydrogen ion or hydronium ion and the anion. So these go, if you looked at the equilibrium constants, these would be huge for these because they go about 100% to completion. Weak acids, though, do not completely dissociate. They mainly stay in their molecular form, and as long as it's in the molecular form, we don't get the properties of an acid, because what makes an acid is that free hydronium ion. So again, we talked about this in Chem 140, that how do you transport concentrated sulfuric acid from, like, say, Texas up to Michigan to make plastics for the dashes inside automobiles? Well, we can put it in a tanker car, but we need to have it almost 100% pure sulfuric acid, so there's no water there for the acid to ionize into the hydronium ion. And so as long as it stays about 100% pure, you can transport concentrated sulfuric acid in a tanker car. But if you ever notice that when one of those tanker cars derails, it's a big problem, because once that cracks open, we'll start pulling moisture out of the air, and now we do have a strong acid present, and that's going to be an exothermic reaction. We're going to see a huge vapor cloud. So you've probably seen that in the news, like where a sulfuric acid tanker car derails, and then it's a real problem. But as long as the acid stays in the molecular form, we do not have those properties of an acid yet. And so carboxylic acids, like it says, they only dissociate to about 5%, so they are considered a weak acid. Doesn't mean they're not important, but they are considered weak. All right, so I don't know if you remember, I don't know if you've done this or not, but a common thing we do in Chemistry 140 is a titration reaction, where we'd like to know how much acetic acid's in vinegar. So most vinegars are about 5% acetic acid, and then the rest is mostly water, but there can be some other things in there as well. But so maybe you've taken an Erlenmeyer flask, it looks something like this, and you added some acetic vinegar to it, and then you used a burette. Looks like a long tube. It's got a little valve on it here called a stopcock. And you know what the concentration of the sodium hydroxide is in the burette. And you open this valve, and the sodium hydroxide flows out the tip of the burette. And inside this Erlenmeyer flask, you have vinegar, and then you have an indicator like phenolphthalein. And I'm running out of room, so I'll just say it like that. All right, and so it's colorless. Phenolphthalein is colorless in an acidic solution, and you add enough sodium hydroxide that it eventually consumes all the carboxylic acid. And once all the carboxylic acid is consumed, the sodium hydroxide reacts with the phenolphthalein, and we see a pink color. That's our endpoint. We stop the reaction. So then we know what the volume of sodium hydroxide dispensed was, and we also know what the concentration of sodium hydroxide was in molarity units. And so we can determine how many moles of sodium hydroxide we dispensed in the reaction, and from that, and using a stoichiometry, we can determine how many moles of the carboxylic acid that was in the vinegar, in this case acetic acid, and we can so we can determine the molarity of the acetic acid in the vinegar. All right, so that's what this is about. You take a carboxylic acid, and again, like I said, the most common titration is probably acetic acid, but it could be any of the carboxylic acid. You want a strong base, and the reason why you want a strong base, you want this reaction to go 100% to completion. You don't really want something that's kind of oscillating back and forth, or it's not quite making a. It's not. I don't know if I want to say oscillating. I just want to say you want it to go 100% to completion, and you want it to happen fast so that you get a nice endpoint. That's the best way to say that. So again, as long as carboxylic acid is present, sodium hydroxide removes the hydrogen ion from the carboxylic acid. With using the hydroxide ion, and we get water, and then what's left over is this carboxylic acid salt. All right, so a lot of times when we do this reaction in Chem 140, we don't write the sodium ion because it's not really that important to us, but it actually does two things for you. First of all, it shows you that this side is charge neutral. You got this negative ion, and then you have the positive sodium ion. But what we're going to find out is these salts are really important in themselves, and so that's why they're emphasizing, oh yeah, the sodium. And again, this is this carboxylic salt. If it's water soluble, which it should be, it actually is dissociated. It's not. They're not attached. But if we would evaporate the water off, you would be left with an acid salt. You have these crystals of acid salt left over. All right. So one other thing to remember is it says equilibrium shifts to the right with the removal of the hydrogen ion. Again, as we that's what's happening, right? The hydrogen ion's removed from this, and we've formed these products over here. All right, so this is an important slide. This is one of the things we do with carboxylic acids, acid-base titration or a reaction. This is called neutralization because here you have an acid, here you have a base, and you're going to end up with the salt and water. And remember in Chem 140, we talked about neutralization reactions, that type of reactions when an acid and base react and form water and a salt. All right, so yeah, here's the, again, most common titration I know of. Acetic acid reacts with the strong base sodium hydroxide. We get sodium acetate, the salt, and water left over. But we could also take something like benzoic acid. So we have benzoic acid, and we add sodium hydroxide. Same thing happens. The hydrogen reacts with the hydrogen ion reacts with the hydroxide ion. We get water. And then what we have left over is sodium benzoate. And that's going to be an important compound. Sodium benzoate used as a preservative. It's in a lot of food items. I've seen it in candies. I've seen it in toothpaste, I believe. Let's see. those are the two things I think I've seen it most of the time. But you can look on some of your food label items. That'll be a common preservative. All right, so when we go to name a salt of a carboxylic acid, it's more like, just like we learned in Chem 140, it's this is an ionic compound, and so you name the metal by its full name, sodium, and you name the anion, which is the negative ion, which is the in this case the benzoate ion. All right, so the oic acid becomes an 8 ending. All right, so it kind of works the same way. If you remember, in Chem 140 we said ic ions make 8 acids, and I said that the way to remember that, the mnemonic, the memory device to help you remember that, is I ate something icky. So ic acids make 8 ions. I ate something icky. All right, so there's sodium benzoate. What we're going to find out about these salts is, the big one right here is soaps. Soaps have an ionic end on them, and it also has a nonpolar end on them. That's the long chain hydrocarbon. And so the nonpolar end is going to help dissolve dirts and oils that are in your clothes. Like, say you're washing your clothes and you put some detergent in, and the ionic end will dissolve in water. So the nonpolar end surrounds the dirt of and oils in your clothes, and that causes that to dissolve off of the clothes. And then once that micelle, that large molecule that has all of these sodium benzoate or whatever carboxylic acid salts attached to it, on the outside of that you're going to see it's mostly polar. It's got the polar end, and that dissolves in the water. So that all goes out in the water as the valve opens on the washing machine after you've washed the clothes. Then you rinse off whatever excess you have left over. So you have the wash cycle, and then you have the rinse cycle, and hopefully you didn't add so much soap that it's not completely removed, or most of it's not removed with the rinse cycle. So you don't want too much detergent in your washing your clothes, but you want enough to remove the dirts and oils from your clothes. Maybe we'll see a slide on that. It's also a preservative, antifungal medications, also used to control food pH. All right, here we're going on to our next group of compounds called esters. And carboxylic acids react with alcohols to form esters in water. All right, so what's an ester look like? Well, the first thing you want to know about an ester is it kind of looks like an ether, but then you've got this carbonyl group here. All right, so when we look at that on the ester, that's what's going to be a big difference here. You still got the O, but you've got a carbonyl group. So that's what you want to use as a distinct difference between an ether and an ester. All right. So what we have here is you have alkyl group 1. We have a carboxylic acid, the whole thing. All right. And then we're going to react that with an alcohol. And there's this is alkyl group 2. Could be a methyl group, ethyl, propyl, whatever you want there. So when you react that in an acidic environment, that's going to remove the hydrogen. So it's an oxidation here again. And so this oxygen still wants to bond with some, so in comes the other alkyl group and bonds with that oxygen. So you're substituting this hydrogen here for an alkyl group. All right? And that's going to make a wild group of compounds that you come in contact with probably on a daily basis. This is what makes bananas smell like bananas. So a lot of your esters have very distinctive odors, and they're fruity a lot of times. They can be different things, but you generally think of mint, fruit, and things like that. All right, so esters are mildly polar. You go, why are they mildly polar? Well, they've got that carbon double bonded to an oxygen, and so this is partially negative and the carbon's partially positive, so there's the mildly polar. Because they're mildly polar, they're somewhat water soluble. Now, again, the longer those alkyl groups get, the more insoluble it's going to be. Again, generally found in food, and it is kind of what makes your nose go, oh, I really like the smell of this, and I want to eat it. All right. So here are some of them. Isoamyl acetate, again, that'd be the common name. Banana oil, 3-methylbutyl ethanoate would be the pineapple, smell of pineapple. And then we have raspberry. And so here's the key right here. They do boil approximately the same temperature as the carbonyls with comparable molecular weights. All right. So that tells us this is the really important part of an ester. I mean, yeah, you have to have this oxygen. You have to have this for it to be an ester. But this is the really important part right there. So it's going to determine the physical properties. All right, so here's the advantage of the IUPAC naming. So it says use the alkyl group as the first name, alcohol part of the ester. All right, and then base the name for the acid part of the structure from the longest chain ending in the carbonyl group. All right, and so. And then change from a carboxylic acid, like ethanoic acid, to an O8. All right. Okay, so we have ethanoic acid. So this is our carboxylic acid. This is our alcohol. The acid's going to take this hydrogen off. All right. We're going to attach this. Oh, yeah, I did that wrong. It actually takes off the whole thing and forms water. Why did I do that? Yeah. So the hydrogen from the acid, the hydrogen ion from the acid, and the hydroxyl group from the carboxylic acid is removed. And so then what we get is this methoxy group attached to this ethyl. I mean, we could say ethanoate. And so because remember, this is the carboxylic acid now. I mean, it looks like that part of it, even though this oxygen came from the alcohol. So you name it by the alcohol part, all right, methyl, and then the ester part, which was the carboxylic acid, becomes from ethanoic acid to ethanoate, all right. So carboxylic acid becomes from oic to onate, and the alcohol is going to get us the first part of the name there. All right. So for this one, we know this is part of the alcohol, and this would be the part that came from the carboxylic acid. So we look at this part. This is from the alcohol, ethyl. We had a OH there. It would be ethanol. And so this attaches to this 1, 2, 3, 4 carbon long. So that's 4 carbons of butane. Carboxylic acid would be butanoic acid. And so we would call this ethyl butanate. All right, that would be the IUPAC name, ethyl butanate. All right. Same thing here. You got the long chain alcohol. We know this came from the alcohol, and we know this part comes from the carboxylic acid. And so that's ethanoic acid, also known as acetic acid. But again, we're going to use the IUPAC naming here. There are going to be some common names we need to know. But this one, again, going by IUPAC, this would be, this is three carbons long here, so that's propyl. And this is ethanoic acid, or that's the original part that came from. So this would be propylethanoate. I'll just tell you to practice a lot on the naming. There's plenty of problems. It's in your Connect assignment, and it's also in the back of the chapter. You'll find when you can just look at them and bam, 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 then you know them. If you're kind of struggling and you find like, oh, I look at it and then I look at the answer and you don't get it right, and as long as you keep doing it that way, you haven't really gotten it down yet. So that's how you're going to gauge, do you understand how to name these? Do plenty of them until you just hit them right off the bat with the right answer. If you're not getting that, you haven't really comprehended it yet. All right. They make a big deal about this part. Yeah, the salt generally is written this way. I would agree with that. But, I mean, hopefully you recognize this is just an ionic salt, and you always name the metal first and the polyatomic ion second. So sodium ethanoate. Again, here's the problem with this. Yes, sodium ethanoate, I'd love everybody to call it that. Again, IUPAC name, and you can see, I think you can see by now, IUPAC, it's got a very systematic way of naming, and once you get it down, it's easier to transition from one functional group to the other. But this stuff is still called sodium acetate. I mean, if you ask most people, they're going to call this sodium acetate. So the common name is still used quite a bit. I would say even probably in America, it still dominates. I think sodium acetate is what you would hear. But again, the IUPAC name, I think it eventually will change. It'll make it much easier. All right. I don't know, though. We haven't changed to the metric system yet, so I don't know. Who knows? All right, so what's reactions involving esters? Well, first of all, just how you make it, the esterification process. So, again, this is a dehydration process because, again, what's happening is we're removing the hydroxyl group from the carboxylic acid and the hydrogen from the alcohol that's forming water here, and then this part attach, and we get the ester. All right. The key here is, and this is where it gets a little complicated, make sure that you get what it is required here, because sometimes I see that as a question on quizzes, and you'll probably see it on the assignment. It's not only that you have to have an acid, you also have to have heat. Acid and heat are required for this reaction to happen. All right, so again, by this point, we're getting to be pros at this. We know this alcohol is going to lose this hydrogen. We know that the carboxylic acid is going to lose this. And what's going to happen then is this carbon is going to attach to this oxygen and this alkyl group, in this case ethyl group. And so to name this, we look at the carboxyl group, which is 4 carbons long, so we know that this is butanoate. And then the alcohol was an ethyl alcohol to begin with, or ethanol. That would be the more IUPAC name. And we call this ethyl butanate. Again, this substance, you hear it called this a lot too, ethyl butyrate. It's going to happen, and the reason why is because, again, biology, they would generally probably use that term versus the IUPAC term. All right. All right. I think you, again, we know this comes off. We know this comes off. Those attach. Again, the key that tells you it's an ester is this part right here. That's what you're looking for. Okay, hydrolysis or hydrolysis. I used to say hydrolysis. I think I use I used to say hydrolysis. I think that's what I was taught by inorganic chemists, and that's what they would say. Your biologists are definitely going to call this hydrolysis, so I can go with that. So what that means is hydration. We've seen hydrolysis before. It's where when we add something like sodium chloride to water, and sodium chloride is an ionic compound. When we add it to water, we get separation of the ions, like so. And we said, well, how do these ions stay apart? Because this positive's got to be attracted to this negative. Well, remember, in water, what happens is the water molecules, the oxygens in the water molecules form a cage around the sodium so that the sodium ion cannot get back to the chloride ion, and that's why an ionic substance like sodium chloride dissolves in polar water. Remember what's going on here is each one of these oxygens is a partially negative charge, so it orients itself around the positive sodium ion, and then the hydrogen ions, being partially positive, orient themselves around the chloride ion, and again they form a cage around the chloride ion so that the sodium ion and chloride ion can't get back together. So that's called a hydration. Cleavage of any bond by the addition of water molecule. All right. So we separated those, cleavage with the water molecules. All right. Since, however, the uncatalyzed reaction is slow and requires heat. Now, here we're talking about esters. Again, in order for esters to go this reaction, it needs some acid or base and be catalyzed with heat. All right, so we have an ester, we have water. Again, here's what's going to be the key. You got to have not only an acid, but you also have to have heat. So, hydrolysis, hydration means we're going to be adding hydrogens to the ester. So you can see right here what's going on is this is going off, and it's going to react with the hydroxide ion, or if you want to say hydroxyl group of the water, and we form an alcohol, and then we have a hydrogen attached to the ester, and we get back to the carboxylic acid. All right. So in order for this to happen, hydration, here's the key. When you hear hydration, you should think water. That's what hydration is, or hydrolysis. Then you got to think about what encourages this reaction to happen. Well, here's what you have to have for this reaction to happen in an appreciable rate. You got to have a strong acid and some heat. All right. So really, this is just the reverse. I mean, I guess that's the way I would remember it. I mean, we took carboxylic acid and alcohol, and we went this way, and we formed the esters. And now we're just doing the reverse reaction, ester plus water in this case, starting off with those as the reactants, and we end up with carboxylic acid and alcohol. And again, you get the naming. This one is 3 carbons. Here's our alcohol part, so this would be propanoate. And that forms propanoic acid and 1-propanol, which we can just call that propanol. Again, that's a common name, but again, you should say, I like the 1-propanol. That tells people it's attached to the end carbon. It's this carbon and not this carbon. Okay, we also have base hydrolysis of esters, or hydrolysis. So I'm going to have that problem with this, that you're going to see a let me switch it between those two names. All right, so I just wanted to close the door there. All right, so look at this reaction here. Again, ester and water, so that part doesn't look different. But what's different here is instead of using acid, we're using a base. So you go, why would I want to do that? Well, notice what you get is you get the, we're trying to make the salt of the carboxylic acid. So we're still going to get an alcohol. That part looks the same. But because we're using a base, we're going to get this R alkyl group to attach to the hydroxide group. Or actually, I shouldn't do it that way, probably. I should say it attaches to the hydroxide group of this, and then we get an alcohol, and then we get the carboxylic acid ion. All right. All right. This is the most important base catalyzed hydrolysis reaction. This one comes up all the time. You definitely need to know this one. Saponification. All right. Saponification is soap making. That's what it's about. Saponification. We are going to make soap out of these esters. All right. So where do the esters come from? Well, here's an example. It's a fat or oil triglyceride. So here again, you know, you hear about triglycerides in your body. It's not good. These are fats and oils. I mean, we got 3 or 4 different names for the same thing, right? These are esters. These are fats, oils, triglycerides, all of that. All right. So we can take, you know, if you ever seen them make soap at some of these Pioneer Days or Harvest Festival in Kentucky, they take animal fat, can be either beef or pig, and they add sodium hydroxide, and they heat that up in a big cast iron kettle. That's what this is right here. So you've got sodium hydroxide, and you've got heat, and you got some water here. And that changes this ester into a glycerol. The glycerol is a foundational component of most soaps. If you look on most of your soaps, you'll see that substance, glycerol. It's actually kind of sweet look, and you can see it looks kind of like a sugar, right? If we had another OH group here, or you know, maybe one down here, you'd start saying, oh, that's a sugar. All right, so it kind of looks like a sugar. It is sweet. We would think of it as an alcohol, right? Because it's got the "all" on the end of it. And so from that alcohol, we get this compound over here, which is a mixture of carboxylic acid salts. All right. So we get this component, and it's negatively charged, and then we get the positive metal ion here. So like sodium ethanoate or sodium propanoate. All right. So this is what makes a soap a soap. Again, this end of it is nonpolar. This end of it's ionic. So this end, where this nonpolar part is, dirt and oils, which are also mostly nonpolar, dissolve based off of this alkyl group here. And so you have this piece of dirt, and then surrounding it, I'm going to just say R groups, and then out here is the O negative groups. So these R groups are attracted to this other nonpolar end, and so you get a bunch of soaps attracted with these O negative groups on the outside, like so. So the dirt's encapsulated in here, but on the outside, all we see is these negative, partial negative or negative charged oxygens. So that part's, the outside is going to be attracted to the polar water, like so. Remember, water partially positive on the hydrogens and partially negative on the oxygen. So the dirt's in here, surrounded by the soap, and then out here on the outside, it's these negative charges, and so that entire cell, as it's called, a micelle, dissolves in the water, goes out with the rinse, and you've got clean clothes. Well, and they draw a nice picture of it. Here it is again. Dirt here. Here's that long chain. Here's the non-polar end here. I mean the polar oxygens here. Or I should just say negatively charged oxygens. This one's a little. They've got theirs done a little differently here. Now, you say, what's going on here? Well, they're showing that metal ion, I guess, because these should be oriented. Yeah, this isn't quite right. If these are the negatively charged oxygens, let's make that. If these are the negatively charged oxygens, then the hydrogens ought to be oriented towards those oxygens. All right. So where do you see this? Sometimes these things don't dissolve very well if the chains get longer, and you see it as soap scum, or you see it as these big foamy messes at the bottom of a waterfall. Some of that's caused by this soap interacting with water. All right. This slide is about condensation of polymers. So here we're taking so polyester is a condensation polymer. I think I would memorize that. You need to know that. And when you remove something like water, it starts linking together and forming a chain. So let's look at that. That's what a polymer is, right? So let's look at this. This is the one I talked about when I posted the announcement in Blackboard. So here we're going to make PETE, polyethylene terephthalate. Again, that's a common name. And this is what makes the plastic bottles that your soft drinks come in. All right, and you know they're pretty tough. You can drop one of those bottles; it doesn't explode. Maybe you've done the YouTube video stuff where you take Mentos and drop them into the Coke and it shoots out as a fountain. So those bottles are pretty durable. The only thing about those bottles, they're not really reusable. You can't like heat them up, clean them out, and reuse them. All we can do is recycle them. That's the downside of them. So they're great for one-time use. Put pop in them or soft drink, but they also have problems as well. But this is the process of making this PET, which is a polymer. Now, what is a polymer? It's a repeating unit over and over again, and that forms strands, and those strands then can form, as we make them longer and link them together, we get something like the plastic bottle. All right. So here we have, it's an alcohol, right? But it's got two OH groups, so that's called a diol. We've had that before. So again, if you're struggling with that part, if you can't call this ethane diol pretty quickly, it means you got to go back. You got to go back and look at the chapter on alcohols. All right. So what do we have over here? Well, over here we have a carboxylic acid, right? And it's a dioic acid, right? Because you got two carboxylate ions. So there would be another name for this. Than terephthalic acid. What would it be? Think about it. Look it up. All right. So what do we have here? We're adding strong acid to that. What's that going to do? It's going to cause this this hydrogen to come, this OH group to come off here, and then we lose this hydrogen here, and we're going to form water, and then that's going to bond together, and we get this compound. All right. Now, where the chaining comes in is we now have this OH group here. We can add more terephthalic acid, and we get a link here. So you see this keeps forming where the hydrogen OH comes off here, and we get a carbon double bonded Yeah, we get a carbon double bonded to. So what we see here is that OH group coming off. All right, and an H group coming off the alcohol, and so we see this repeating unit here. All right, so that's a polymer. So again, here's the hydrogens coming off, dehydration, and then off of the alcohol, we're getting a hydrogen off, and hydrogen off there, and so that's where the links can initiate. All right. All right, we'll stop here. I know we just got a few slides left, but this ought to be treated separately because we're doing a different reaction here. So we'll stop here for this video.